I'm happy to present Yoshua Bengio from University of Montreal and Mila.
My talk today is about something maybe milder than like consciousness, just conscious processing. The things we know in terms of the computations going on in our brain, we know are like hypothesized and has been, for which there's quite a bit of evidence. In particular, I'll talk about the global workspace theory and how we can use that as inspiration for, if you want, neural net architectures in machine learning that can lead to better generalization. So that's what I'm going to talk about. Okay, so I'm a machine learning researcher, and the central question in machine learning is generalization. How do learning agents manage to generalize, and what are the current limitations of our approaches that we use these days? And there is an issue that people have known for a while, but that really has come to the front, and one of the hot topics in machine learning these days. And that is the problem of changes in distribution. So you may be training on some data, and then you're going to use your system in a different context, and it's going to fail. So what's going on? Well, first of all, learning theory doesn't give us any guarantee about what's going to happen if you train a system on some data set that comes from a particular distribution, and then you try to apply that on a different distribution. I mean, it could be arbitrarily different from the training distribution. So, what can you say? It seems intractable. And so that's the reason why people mostly have kind of ignored this, but in practice, it comes up quite a bit because they're non-stationaries, like things change in the world. Maybe your training data comes from some country, and then you would like to use it your system in another country. And we know humans are quite good at this sort of dealing with this sort of changes, which is going to be the big theme of my presentation. So one way to think about how we could even possibly generalize, and how humans might be able to do that when the world changes, under your feet, is that there must be something in common between the new distribution and the old distribution, the one we use to train and the one on which we're going to be tested. So that's the kind of question I'm going to be asking, and you can think in a way of like knowledge that you put in books and we communicate with each other. Attempts to be something that is universal, like it doesn't change with time. Like you think about laws of physics, hopefully they don't change as we move forward, right? So these are like the ideal kind of knowledge that is very stable, and that's what allows us to generalize. So as an example of generalization, and I'll use several examples, but imagine out of distribution, imagine you've seen scenes of how things look like in the world around us on this planet, and then you're an astronaut, you arrive on the moon, things look very different, but you're still able to make sense of what you're seeing. And even if some things like the constant of gravity is different, you can still make sense of that. So why are you able to do that? There are things that don't change, like the laws of physics didn't change. Maybe the circumstances in which you are look very different, but they can be explained by the same underlying mechanism, as I'll call it. Right. So, and then the other thing, of course, is, well, humans seem to be doing a pretty good job. I mean, we're not perfect. Of course, we make lots of mistakes, but compared to the state of the art in AI, we are very good. And if you just ask for yourself, you don't even need to do a scientific experiment. What happens when you are confronted with a new situation? Well, what happens is, instead of going by your habitual behavior, you sort of think about it, right? Let me give you a concrete example again. Let's say you're you're used to drive at home in your home city, and you go for a vacation in a different country where the traffic laws are different. Maybe one has to drive on the left versus the right. So initially, when you get in that country and you start driving, you really need to pay attention to what's going on, because if you just go by your habits, you'll probably make an accident. So there's something about attention here. There's something about thinking, and there's something about reasoning, and incorporating like the new rules that you're just told on the fly without having to practice for years, and you're still able to drive. Now, initially, it's going to be very painful. I mean, there's a lot of effort in paying all this attention to every little detail when you're in this new country while you're driving, but eventually you're going to practice and you don't need to think about it anymore, right? So there's a process of converting the reflexive way of taking decisions that's slow and painful to one that is very smooth and actually more efficient, both in time and the sort of the ability to do things right, so long as they're not really very new. So that, to me, talks about the system 1, system 2 division, right? So this is something that was that's been there for a long time in psychology, and I like very much Dan Kahneman's book, Thinking Fast and Slow. So I'm going to use that as an inspiration. Roughly speaking, again, taking the example of driving, you have driving in your home city, and somebody can be talking to you at the same time. You don't need to think about what you're doing. You kind of know what to do. The computations that are going on there are intuitive. In other words, you're not conscious of all the details of what's the reasoning behind why you decide this or that. And in fact, it may be very difficult to explain verbally why you did this or that. And current deep learning is good at that sort of system 1 computation. This is basically the main mode of operation of the current state-of-the-art in machine learning. But if you're in this new city, the system 2 on the right, you don't want the other person to talk to you because you need your attention on the road. And it's going to be slow. You can use logic. You can use like explicit knowledge, like those rules, and you're conscious of why you're doing this or that, and you can explain it to the person on your right. This form of computation is very, is something we use a lot in planning, in reasoning, in writing code, designing algorithms. It's all about explicit knowledge that goes through our working memory and that we can verbalize. So that's what I want to bring in deep learning. So you can call it deep learning 2.0 that has both system 1 and system 2 in it. Okay. Now, speaking about deep learning in the 2000s, when my colleagues and I were working on the early deep nets, one of the things I and we were thinking about, but I was really focused on, is if we're going to be learning these deep nets, and each layer gives us a representation of the data, and we're expecting the higher levels of representation that happen through more processing, more levels of computation in these neural nets to correspond to more abstract entities. And ideally, this would be the kinds of entities that explain the things we observe in the low level, the perception. And then if you go that route, really it's about discovering what are the causal variables that explain the low level perception, like images, and how are these causal variables related to each other. So the picture is like, the one on the right. We have some, it's a very rough picture. We've got some neural net that is able to extract from an image things like, what objects are present, in what relation to each other are they, and so on. And then in order to make a correct interpretation of what is going on, you also need some sort of knowledge about which objects tend to be with each other or in what spatial relation to each other and so on. And that's represented by some sort of model of the world that is at this very high level, abstract level. And we would like our machine learning systems to be able to do both things, to learn how to extract those high level variables and also figure out how they're related to each other. When you start thinking about causality, there are other things that come up that have to do with my original question of changes in distribution. So in the literature on causality, the way we think of changes in distribution is as being caused by what we call interventions. Like somebody did something, like you went to a different country, or there was an accident, and that now you have to take a new path. So you need to also take into account these interventions, because they basically, if you capture that, then you can deal with changes in distribution, because they're really, it's just really the same model. The world hasn't really changed. The causal mechanisms haven't changed. It's just that some elements in it have changed. And sometimes which have changed. Sometimes, like the rules have changed, the rules of the traffic, or something. Sometimes you don't know, and you have to figure it out from the data. But there's this notion that there is also these random variables that tell us about the actions that have happened that may yield apparently very different images, say, and you need to take that into account. There's also more complications, like the interventions may be something very abstract, like I'm going to go to a different city, but to implement these interventions, I may need to learn a low-level policy, like how to move my muscles, like there's the whole motor control. So there's really abstract actions as well as low-level actions, in the same way somehow that there are like high-level perceived entities as well as low-level things like pixels. Okay. So one way to think about how a causal understanding could help a human make sense of the world, let's go back, for example, to my going to the moon scenario. So there, the laws of physics are the same, but things look very different. Why is it that they look very different? Well, one way to think about it from a physical perspective is, even though the laws of physics are the same, the way things are organized on the moon, like the conditions, how there's no atmosphere and whatever, and the gravity is different. So the conditions are different, and because of that, even though we apply the same mechanisms, we get different observed data, and the distribution, more importantly, the distribution of these observations may be very different. So one way to think about this is when we learn about a distribution, instead of just focusing on, okay, we're going to model the data, if we can factor that knowledge about the distribution into the things that don't change, like the laws of physics, the causal mechanisms, and the thing that may change, like actually, the gravity constants can change. If we can factor these, then we are in a good position as a learner to face those changes in distribution, because now we don't need to relearn all the stable stuff, the mechanisms. We only need to make inferences about those maybe initial conditions or things that have changed. All right, so let's go back to humans a little bit. For most of my presentation. So if you follow the ideas about system 1 and system 2, we can think of it like you have knowledge at both levels, right? We have like system 2 knowledge and system 1 knowledge. So system 1 knowledge is you know how to drive, but you can't explain it, but you do a pretty good job. And system 2 knowledge might be things like the traffic rules and, you know, kind of in a way that's explainable to other people, how you should behave on the road and things like that. So these are two different kinds of knowledge. And where this could become interesting for a learner, like a human and future AIs, is that these two kinds of knowledge may be obey different constraints. So in particular, the system 2 stuff, the stuff that is verbalizable, well, if it's verbalizable, that's a very strong constraint. Like, you know, you make sentences, they involve very few words. That's very different from the kind of knowledge you have when you recognize a cat from an image, where you're taking 1 million pixels and combining that in order to come up with some decision. Whereas these high-level things like sentences, they involve just a few words. So there's a notion of sparsity that I'll come back to. So there are assumptions about how the random variables are related to each other that may be very different at the system 2 level than the system 1 level. So, you know, why would that be evolutionary interesting? Well, if some aspects of the world are in a way simpler because they have, for example, these sparsity properties, then, and other aspects don't, then it would make sense for evolution to figure out a way to discover how the world works that separates the things that are kind of simpler, the things you can verbalize, from the things that are, well, not easy to verbalize. And so you can exploit, at least at the level of system 2, you can exploit those inductive biases, so these assumptions. In other words, it's an interesting way to deal with the problem of inductive biases. So biases could be good or bad. Like if a learner assumes things and they are wrong, then the bias becomes a problem and you make mistakes. But if the bias is roughly right, then it makes learning easier. In fact, could be exponentially easier. It could be way easier if you have the right biases. And so, yeah, so it makes sense for a learner to sort of separate the part of his knowledge that has some biases that really make learning much easier. And in fact, we can learn at this top level, we can learn very easily. You just tell me a new rule and I can just memorize it right away. Whereas my habitual thing, I need like millions of examples. Well, maybe thousands. Okay, so now I'm going to try to go in a little bit greater depth in so what these inductive biases, these assumptions about the world at the system 2 level could be. And mostly we can sort of read them off by looking at how we communicate information with each other through language. So the first one is the one I already mentioned, that the statistical dependencies between those high-level variables are sparse. In other words, I can predict a abstract quantity like the position of the ball from very few other abstract quantities like the previous position and whether I drop the ball or not. And so, for example, if I say, if I drop the ball, it will fall on the ground. What's going on really is I'm representing information about this video of balls, falling or whatever at a high level where the dependencies can be summarized with very, very few variables. And that's a very strong constraint. Like you can't do that on pixels. Like if you try to predict one pixel given 3 other pixels, your prediction will suck. It will be very bad, right? So it's a property that only works for these high-level variables. So that's maybe one of the most important things to realize from my talk. And then if you're doing machine learning, or if you're trying to understand how humans might take advantage of things like that, this is really a property you want to exploit. And in fact, I'll try to argue that this property is consistent with, and maybe even sort of a consequence from the point of view of evolution of the global workspace theory. So in other words, having a bottleneck of communication, your working memory, like 5 or 7 things or whatever, that you can hold in your mind, it enforces sparsity, because if I can only hold 5 things in my mind, then the only kind of dependencies I can represent are between at most 5 things. I can have many such little dependencies, all of the rules I know about the world that are verbalizable, but each of them is very simple, involves very few variables. And having this bottleneck of communication between different parts of the brain kind of enforces it. At least that's my claim. But you can have there are other things you can deduce just by looking at language, natural language. For example, the words in language, many of them seem to have to do, they're not just like abstract, they're also causal. So if you look at typical sentences, it tells you about what caused what, who did it, why, what were the things that happened, the interventions, the agents or the entities that are causing interventions. So subjects, for example, and objects in the sentence typically would be the effects of some action that's given by a verb. So there seems to be a lot in what we say that has to do with that causal understanding of the world. And this is something we can take in machine learning models, because once you say that a variable has a causal interpretation, it introduces some constraints of how you should model things. Also, the same rules, the same high-level form of dependencies, like what happens when you drop an object. Here it was about a ball, but I could use the same rule and apply it to other objects, right? So there's a very powerful prior here, a very powerful bias that says we have these generic causal mechanisms, like what happens when I drop something, and they can be applied, they can be reused all over the place, wherever they're relevant. I don't need to learn a separate conditional probability for every possible set of objects that I'm going to drop. That's mostly the same thing that's going on. So that's extremely powerful, and it introduces a constraint in the way we design machine learning methods, because now you want to sort of pull out these shared pieces of knowledge, like rules in classical AI, right? The same rule could be applied to many variables. It even introduces a notion that, well, we have variables, like arguments in code. You have a function, the same piece of code that is a function has arguments, and I can apply that piece of code to many arguments. That's the same inductive bias. But we typically don't have these constraints in our state-of-the-art machine learning methods. And it's very powerful. It allows us to generalize to new objects. And we don't even need to know what the object is. If I say, if I drop the zog, it would have fallen on the ground. Well, you immediately know that a zog is something that I can hold in my hand, and it's probably small, for that, and it's an object. It's already like a lot of knowledge that you can infer just by the context. So you can generalize to completely new things because of that factorization of knowledge. Another inductive bias has to do with the discreteness of the high-level variables. So I'm not saying everything we think is discrete. I don't know the answers to that question. I have the impression that my thoughts are often like geometric and have shapes and stuff that seem continuous, but a lot of what we think, a lot of what goes through our working memory is discrete, is symbols, right? So symbolic AI, of course, has kind of exploited that. But what happens when you say that in the global workspace theory, you have different parts of the brain, different experts that are communicating through the working memory. So if the things that they're communicating are discrete, does it buy you anything? Is there an advantage? And so we have a paper that explores this. And what we find is, indeed, if you have a bottleneck of communication between the brain modules, I mean the neural net modules, and those messages being communicated are discrete, it yields better out of distribution generalization. And one way to think about why this may happen is that it makes these experts more hot swappable, right? So, in language, I can replace a noun by another one in a sentence, and you still kind of make sense of it. So it's the same thing. More generally, if there are very few bits that allow me to describe the message, it could have come from a different expert. Like, there's an expert for this noun, and maybe there's another expert for another kind of noun. But in many sentences, any of these experts could be doing the communication, and the rest of the brain would still understand, because it's like they speak the same language. The language is simple enough that it's easy for them to coordinate to make that kind of universal across these experts. That idea of a communication language is actually right off the initial papers from BARS. But the new part, the things that my group is doing, is exploring how we can take these inductive biases and stick them in our state-of-the-art machine learning systems and see what happens, and also try to understand the sort of mathematical reasons why it may be advantageous. Another very powerful inductive bias is that the changes in distribution, which was, again, this is my starting point, like trying to be robust to those changes. These changes in distribution, if you buy the sort of causal interpretation of things, they are very sparse, meaning, there's maybe just one variable that changed. So when something changed in the world that changes the distribution, like I go from Earth to the moon, there's basically only one variable that changed, like, which planet are you on? Or if I go from Montreal to London, driving, the driving example, again, there's only one thing that changed, which is which country I'm in. And there are many problems of changes in distribution where typically there's only one thing that changes. And the reason is the changes happen because an agent did something, and the agent can only influence a few things. And then of course there could be side effects, but the initial intervention could be very localized. And that's going to make learning and adaptation to these changes in distribution much easier, because I only need to figure out, well, what was the change? And if the change is only about one variable, I need to just figure out what is the variable and what was the change. Whereas if it could be anything that changed, as like many things could change at the same time, I basically need to relearn my neural net for going from Montreal to London. And that's going to be painful and very long. And I can't afford that, because otherwise they're going to die in an accident. So having this is a very powerful, survival advantage. It's a prior. It could be wrong. Like, we could live in a world where things change in a way that's not so simple, and then we would be screwed, basically. Okay, so these were the inductive biases. Now I'm gonna go and just highlight a few papers that we've worked in the last few years that try to exploit these things, and then tell you about what we're working on now. It's going to go a little bit too fast because I just want to send the message that, okay, we've tried these things and they all bias something in terms of better out of distribution generalization. So the first paper we did in 2019, and then it was followed up by other papers, was about this locality of intervention. So if you assume that the change due to an intervention, the change due to, when there's a change in distribution, you can like pinpoint it to just one little part of your model, then you can get faster adaptation. And we come up both with a sort of rational why this would make sense mathematically and simulations that show that it works. And in fact, you can use this to discover the causal structure. In other words, to figure out whether A causes B versus B causes A, because one of them is going to have the change happening in only one of these parameters, whereas if you have the wrong causal graph, the wrong causal direction, then you're going to need to change more things. So it really hangs on the assumption that the changes are localized. If they weren't, then this would be useless as an inductive bias. In fact, it could hurt. But because typically in the world, this is how we think is going on, it's actually an evolutionary advantage. Oh yeah, this was published at the ICLR 2020. Called a meta-transfer objective for learning to disentangle causal mechanisms. And then, other papers I'm not going to talk about followed up on that. A more recent paper, sorry, the graph is not very good, but what matters is the stuff we can read here. If an agent is going to learn like the causal structure, just like in the papers I mentioned, there are two scenarios you can think of. Like, one is the agent is passively observing those changes in distribution and trying to recover from them. I mean, to adapt to those changes. So that's what I was talking about. Or the agent could be like a child that is actively trying things, is actively changing things in the world, actively doing interventions, and then seeing what the outcomes are. And you could be very random in those active interventions, and that would not be very useful. Or you can learn how to pick your actions so that you will have as much information for the learner, as much improvement in its ability to learn further from the results of these experiments. Right? So this is a big theme, and we have lots of work that I want to talk about that explores that direction. In fact, applies these kinds of ideas in scientific discovery. I mean, to basically help scientists to do experimental design and design experiments that will help as quickly as possible figure out things we don't know, like which drug should be used to address this particular problem. Another line of papers arises from this one called Recurrent Independent Mechanisms, that was put out on 2019 and published in 2021 at ICLR. And so this one exploits the idea in the global workspace theory that knowledge is broken down into little pieces, just like rules in a classical rule-based DI system. So in the neural net world, one way to think about it is we have lots and lots of these experts. Each of these experts is like a little recurrent network, but why this is not just like one big recurrent net is because we're going to put a constraint in how they can communicate with each other. In the first paper, we just allowed any of these expert recurrent net to talk to anyone, but through very few bits of information. I mean, very few experts were allowed to talk to very few other experts. And then in later papers, we actually use a bottleneck like the working memory, where there is a competition between the experts to decide which of them is going to be allowed to put stuff in the working memory. And then whatever is in working memory becomes available as a message broadcast to every other module. And that's straight from the global workspace theory from BARS. Yeah, so that's the version where we have the explicit bottleneck, and it gives better out of distribution generalization. I'm not going to have time to talk about the experiments, but these are fairly simple experiments. You can think like almost like psychophysics for a machine learning system, with things like balls and moving around rooms and stuff like that. And a more recent paper, which I think now is being accepted somewhere, I forgot where. We called it Neural Production Systems, is just expanding on the same theme, where now we think of it's not just that we have different experts, but the experts can decide what elements of the working memory they are going to operate on. Right? So it's not just the selection of which expert is going to talk, but think of the experts as different rules, and each rule may operate on different variables. So given what is currently in working memory, there's going to be a competition between all the rules to decide which rule is going to win the competition. And the rules that find in the working memory things that they like, because they makes those rules relevant in the current context, are more likely to be triggered. So there's a double competition here, kind of double selection, which rule and which arguments from the working memory are going to be used as input for those rules. So we explored that theme. In all of that line of work, it's all the standard differentiable end-to-end triannual nets. It's just that we introduce these particular architectural structures, and we use, for these competitions, for example, we use what's called soft attention, something that my group introduced in 2014, and that has really transformed natural language processing with neural nets and become the state of the art in neural nets, where there's these competitions, but they're soft competitions. So it's not like actually there's only one winner. You have like several winners, and they win to different degrees, and then you're able to propagate gradients through these choices. And so all of these things are trained by backprop and all that. The other paper, sorry, my slides are not up to date. That was presented at the last NeurIPS. And that's the one I mentioned where we introduce not just a bottleneck of communication, but force discretization of the message. And so there are many ways of doing that. And we can think of it like there are different entities, like think of words, but they are, you actually have like real valued vectors for each of these entities. They have like detailed information about these entities. Maybe they're like descriptions of objects you're seeing in the input. But in order to send information about these entities from through the working space, the working memory, you're going to discretize them. So there's going to be a code book, like a table that says, well, these are the concepts I know, and this is the sort of the typical value of these embeddings, these vectors for each of these entities, and whichever is closest is going to win the competition. So the thing that is being sent is just the ID of the code. It's not the whole vector, right? It's just a symbol. So the modules communicate with each other through these symbols. And again, we see improvements on various tasks that people have been putting up for out of distribution generalization testing. All right. Now let me move on. So these were things that we've done. And now let me tell you about things we're currently doing and where we're going in more or less the next 10 minutes. So where we want to go is extend this work to neural nets that can do, as I said, both system 1 and system 2, and that means they can reason, they can plan, and I'm going to argue that there's a way to do this in which the system 1 neural nets are used to generate candidates, which you can think of thoughts for explaining what we're seeing or solutions to a problem you're trying to solve. And then there is going to be another part which is new, but corresponds to your system 2 knowledge, like all these rules that can be used to check whether these proposed or imagined explanations or imagined solutions to a problem are coherent with the things say these rules. So we now are going to be thinking about two representations of the same knowledge. One that is something that allows you to take decisions quickly and propose the solutions, and maybe you can just directly act on them. That's like you have an intuition and you just act on it. Or you have a different kind of knowledge that can check whether these intuitive generated solutions to a problem or explanations make sense. But you have to stop a little bit, right? And before you act, kind of think about your own thoughts, like let them resonate to see if they make sense with the other things you know. And if they don't, then you might not act on it, and you allow something else to be generated, another possible solution. So this is the kind of scheme that I'm going to propose for neural nets that can learn to reason and plan. And the things that are generated, that are little pieces of information, that's what goes through the working memory. It's very small at each time step, and so it's still with the same kind of inductive biases I've been talking about. And the role of attention here is to select what are the pieces that go into working memory. It hasn't changed, but it's going to be hard attention. So what we mean by hard attention is there's going to be a discrete choice, because we know again from cognitive neuroscience that you don't really have in your thoughts a soft mixture of or a number of different explanations. Like, the Necker cube is either one way or the other in your mind. Of course, you can flip from one to the other, but it's not like you're seeing simultaneously all of the possible interpretations. You see one at a time. So there's like a hard decision, maybe stochastic, that is made at each time step about that, you know, where attention is, what attention is selecting. So that's different from what I've been talking about, because now we can't just do this end-to-end training with differentiable stuff, because we're going to have these discrete choices and these stochastic discrete choices in the middle. Okay. Oh, I forgot this. I should have put this slide before. So as we go in this direction, basically we're trying to do a lot of the things that classical AI, you know, symbolic AI, rule-based was trying to do, except we want to do it, you know, the learning way. So we want to continue benefiting from the advantages of modern machine learning that we don't get with the classical. You know, we want to be able to learn at large scale efficiently. We want the high-level symbols to be grounded in low-level perception. Okay, that's like the symbol grounding problem, which you get for free, you know, in the System 1 world. You want to keep the notion that these symbols actually have a rich representation. They're not just like an ID. They're also represented by these vectors that, like what I've talked about up to now. All of the discreteness is associated with also these rich embedding vectors, which are very common in modern like deep neural nets. Also, we're going to be able to come up with answers very quickly. So we don't need to do the typical search that you have in classical AI. Okay, so which rule should I apply in which order and which rules? And, you know, there's an exponential search problem in a typical classical AI. We don't want to do that. I mean, humans don't do that. We don't spend like, you know, a million thoughts to decide what to do next. We are able to come up quickly with good candidates. That was what I was talking about in the previous slide, and potentially check them and improve them. But we don't need to try in our mind a million things like currently is going on. If you know the classical search-based chess or Go playing, whereas the you know, deep learning, deep RL way of doing Go and chess this day, which works a lot better, is you're also learning this, training this System 1 thing that proposes, you know, do this or do that, and then you can use something that looks a little bit like thought to verify that it works, but you can have a very fast, efficient search. And of course, you also want to be able to handle uncertainty, you know, be probabilistic about what you're doing, which is, it can be done also in the sort of symbol world, but typically leads to intractable computations. Right, so we want to keep all these nice features from the current deep learning, but we want to bring in all the advantages that we see in the classical AI world, like the fact that knowledge is broken down into these small pieces that can be exchanged, that can be composed in order to form, you know, answers to questions and solutions to problems, and that leads to systematic generalization, right? So you can see a new sentence you've never seen, but because you understand the words, you understand how the words combine, you can make sense of it right away. And it may be harder, you know, even with the biggest amazing language models that we have, like GPT-3. Sometimes it makes really stupid mistakes that any bit of, you know, a little bit of reasoning would have avoided, but they don't reason. They're like just System 1. Based on a lot of examples, they kind of know typically what to do in different circumstances, but there is no reasoning step. And of course, as I mentioned, once you do this separation between the sort of generic rules and how they're going to be applied, that introduces notions of indirection and variables and instances and references and stuff that we have in programming and in classical AI. Okay, the last 5 minutes, I'm going to tell you about a new research direction that gets me super excited, that we started less than a year ago in my group called GFLOWNETS, for generative flow networks. And we had a first paper at NeurIPS, this last NeurIPS. And it's a tool for training neural nets to do the kinds of things you want to do if you want to reason probabilistically. And the goal is to develop this to implement all of the inductive biases I talked about and potentially more. So one way to think about it at a very simple level is, a simple problem is, let's say I had already some rules, but doing inference to decide like which rule to apply to what is intractable. So let's just focus on the search problem in AI if you want, right? So let's say we know the rules in probabilistic language. We know the energy function, like what are the constraints that exist if you were to put some solution together. Like basically you can check that a solution is good. How do you train a neural net that's going to produce good answers, like answers that are consistent with that energy function, that's consistent with those constraints, with those rules? So that's like the neural net in our brain that generates thoughts. And it's like a generative model because it's not always the same thing. It seems a bit stochastic. And those thoughts are also sequential, right? So like they're made of little pieces, one after the other. And I'm going to formalize that as, the set of recent thoughts I'm going to think of as a graph, or more precisely a hypergraph. And that graph has hyper edges, where they're like a generalization of edges that link multiple concepts together. So like if you want, subject, verb, object is like a little piece of graph that says, well, there are these three words, they're connected to each other, and there's like a typical way to see whether they make sense. That's my rule about, how can you use this verb, for example. And the edge in the graph says we are actually applying this rule to these triplet of words. And we can check whether it's good, but we also need to be able to generate answers to questions like maybe, this is part of a bigger sentence and we want to know which rule was applied to explain that sentence, which would be like parsing. So in this picture, they like what I talked about, the knowledge about like these rules, the knowledge is broken down into these pieces, like these rules. Rules and facts, basically, and the thoughts, the accumulation of recent thoughts form a composition of these rules. So think of it like an explanation, and that explanation you can think of as a graph. And these graphs are sampled, so they are stochastic graphs. Like even because of ambiguity or because of lack of knowledge, when I see something, there are potentially multiple plausible explanations. So I need machinery, a neural net, that's going to be able to sample from those plausible explanations. So that's what I'm going to tell you about. And so those GFLOWNETs allow you to do that. And more generally, if you think of those graphs, you can think of them as sets of edges, right? So we need a neural net that's going to propose one element to add to the set, one at a time, like sequentially. And then given a scoring function, which is like how consistent is a potential candidate, a potential graph with the rules that I know, I'd like to change my learner, my generative model, so that it tends to sample things that are more coherent with what I know more often. And so this is what GFLOWNETs do, and like I won't have the time to go into details of this. I prepared more slides than make sense. But just to try to make a picture of what would be going on is you have all of these modules. Each of these modules is like a little neural net that proposes thoughts or pieces of thoughts, and those different neural nets, they compete with each other. And there's the attention is now sampling one of these little decisions about what's going to be the next piece of thought, and that changes the content of working memory. And that's broadcast to everyone. So every neural net now has access to the new, bigger context that includes the new piece of thought. And that's going to condition the next choice of which piece of thought is going to be selected. And that the softmax here implements the competition between the different potential thoughts. And part of the competition may be happening within each expert. like to know to which entity that we have already seen the rule is going to be applied, for example. And then there's also competition between the experts, like which rule, which expert is going to win out. Right. So how is that, helping us with reasoning? And how is that related to the global workspace theory? So the GFLOWNET is a generative model that sequentially produces these thoughts, and each of these corresponds to one of the experts of the global workspace theory having won the competition, as well as its content, which is that piece of thought, changing the global state that all the modules see. Right? So all the modules are like receiving the content of working memory. They remember what has been done recently, and they propose the next thought. So now what's cool is that we have a way to train these neural nets. We've already applied this to a number of problems that much simpler than like full-blown human reasoning, but it's already useful. So the NeurIPS paper shows how we can use these new techniques to train neural nets to generate graphs that represent molecules in the context of trying to search for molecules that have good properties for designing new drugs and things like that. Okay, if you want to learn more about GFLOWNETs, there are a number of papers. There's like 4 or 5 papers already. And there is a tutorial that I wrote that you can get from this tinyurl.com/GFLOWNET tutorial. So that's it. I'm ready to answer questions.
Very much for coming to speak to us. It's just time now, Yan. Bye-bye.
Bye-bye.